Hello everyone and welcome to another video on our own devices. I'm Jin Messier and today we are having a look at a fascinating geometry instrument. This is an Ott Type 30 compensating planimeter, and instruments like these are designed to measure the area of irregular two-dimensional shapes. For example, you might use one of these if you are a shipwright and want to determine the displacement of a hull, or if you're a surveyor or geographer and want to measure the acreage of an oddly shaped parcel of land. Now, there are a lot of different designs of planimeters out there, and I can't possibly cover them all in one video. However, I can go over the history and the mathematical principles behind the planimeter and the features of this particular model. So let's dive right in. Now, before the invention of the planimeter, the usual procedure for measuring the area of irregular shapes was to divide them up into a series of parallelograms and triangles whose area could be more easily calculated. However, in 1814, Bavarian surveyor Johann Hermann invented the first planimeter, which was further refined by a number of others, including Italian mathematician Tito Gonella in 1825, Swiss inventor Johann Oppakoffer in 1826, and even the Scottish physicist James Clerk Maxwell, yes, the discoverer of the laws of electromagnetism, in 1856. Now, most of these early planimeters were of the rolling cone or rolling sphere variety, which continuously integrated x and y coordinates in order to determine the area under a particular curve. To explain how this works, let's take a look at the original 1814 Johann Hermann Planimeter. This device comprises a carriage with a pair of wheels that roll along a linear track and drive this rotating cone. Also attached to the carriage is a tracer point which you move along the curve to be measured. This is constrained so it only slides along the y-axis and is attached to a measurement wheel that is in continuous contact with the surface of the cone and connected to an output dial, basically an odometer. Now, let's say you pull the tracer point down to the measurement datum. The measurement wheel now rests against the tip of the cone, meaning that as it is moved laterally, it will either not rotate or rotate very slowly, which makes sense since you are effectively tracing a straight line with zero area. However, as you move the point outwards, the cross-section of the cone in contact with the measurement wheel increases, causing said wheel to rotate faster. This also makes sense as the farther you move along the y-axis, the greater the area you will sweep as you move along the x-axis. In this manner, the planimeter integrates the x and y coordinate inputs into a single input corresponding to area. Other early planimeter designs were free-moving, with a pair of wide rollers allowing the entire instrument to roll along one axis and a horizontally hinged arm holding the tracer point. In this design, the measuring wheel is a cylinder which, as the arm swings side to side, rolls across the surface of a sphere section connected to the rollers. When the arm is perpendicular to the carriage, the cylinder contacts the center of the sphere and thus does not rotate. However, as it deflects from side to side, the contact point moves towards the edges of the sphere and the cylinder spins faster. Now, most of these mechanisms are effectively variations on what is known as a ball and disc integrator, which is a component found in many early mechanical computers. As the name implies, this comprises a spinning disc and ball or roller that can be driven across the disc surface on a track. The two inputs are the speed of the disc and the position of the ball, while the single output is the rotation of the ball. For instance, say you want to measure the total volume of water through a sluice or channel, the width of which is known. You can connect a turbine or other device for measuring water velocity to the disc, or if the velocity is constant, drive the disc with a constant speed motor, and connect a float for measuring water level to the ball. The faster the water flows, the faster the disc spins, while the higher the water rises, the farther out from the center of the disc the ball moves, causing it to spin faster. In this manner, the mechanism integrates water velocity and water level to yield a two-dimensional flow, which just needs to be multiplied by a constant, the known width of the channel, to yield volumetric flow. A ball and disc mechanism was also used in the famous World War II Norden bomb sight used by the United States Army Air Force. In this case, moving the ball across the disc spinning at a constant velocity allowed the bombardier to adjust the rotation rate of a sighting mirror, which kept the target in the crosshairs and allowed the sight to calculate the correct release point for the bombs. Now, these early planimeters tended to be heavy, bulky, and expensive and could only trace a curve in one direction, typically clockwise, and thus were awkward, inaccurate, and never really popular outside of Europe. However, by the mid-19th century, lighter, improved versions had been developed, with one of the most successful being invented by Swiss mathematician Jakob Amsler in 1854. His design is known as a polar planimeter because its arms rotate around a fixed point and calculations are performed in polar coordinates, that is, angle and radius. However, there are also linear versions of this instrument where one end of the arm slides along a linear track. Amsler's Planimeter was widely copied and formed the basis of many subsequent Planimeter designs, including the one we have here. So let's have a closer look at this and let me show you how this works. Right, so this is an Ott Model 30 compensating polar planimeter. This is based on a number of patents filed in the 1950s by one Hermann Ott and manufactured by A. Ott GmbH. Today, Ott Hydromet GmbH of Tempton, Bavaria, which was founded in 1873 by Albert Ott, father of Hermann. This comes in a nice leather-covered case with a green felt lining and has three main components: the pole arm, the tracer arm, and the carriage. At one end of the pole arm is a cylindrical weight and a little spring-loaded needle that digs into the surface of the drafting table, anchoring the arm and allowing it to spin freely around a fixed point. At the other end is a post with a ball to connect the pole arm to the tracer arm. Moving over to the tracer arm, we have a tracer point fixed at one end and a carriage that slides along the arm itself. Mounted to this carriage is a parallel and perpendicular wheel, arranged such that the whole arm balances on 3 points, the 2 wheels and the tracer point. The parallel support wheel is free spinning, while the perpendicular measuring wheel is connected to this readout mechanism via a worm gear. This horizontal dial indicates full rotations of the measuring wheel, while this vernier scale allows for finer measurements within each rotation. Finally, the ball on the end of the pole arm fits into this socket at the front of the carriage, creating a 2-bar linkage. Now, the original Amsler design had a fixed hinge and the two arms mounted at the same level, looking rather like a nutcracker. However, like the earlier rolling sphere and cone designs, this could only trace curves in a single direction and was thus prone to error accumulation. In 1894, Zurich-based instrument maker Gottlieb Corradi introduced this improved ball joint design, which became known as the Compensating Planimeter. Right, so to use this, you anchor the pole arm in place, set the readout dial to 0, then use the tracer point to trace the outline of the shape to be measured. When the measuring wheel moves perpendicularly to its axis, it rolls, and this motion is recorded by the readout dial. When it moves parallel to its axis, it skids without rolling, and this motion is ignored by the mechanism. Now, to understand how this measurement is translated into area, we need to understand something called the area difference theorem, which is an application of Green's theorem from vector calculus. Imagine we have a line segment, each of whose ends simultaneously traces out a different closed curve. One curve is swept out in the positive direction and the other in the negative direction, meaning the area between the curves is swept in both directions and the signed areas cancel each other out. Thus, the area of this region is equal to the difference between the areas of the two closed curves. If the area of one of these curves is already known, or better yet, eliminated altogether, the task of measurement becomes much easier. And indeed, this is exactly the function performed by the track on a linear planimeter and the pole arm on a polar planimeter. As mentioned before, as the tracer point moves around the curve to be measured, the tracer arm undergoes two types of motion, perpendicular and parallel to itself. When the arm moves perpendicularly, it sweeps out a parallelogram whose area is given simply by the product of the arm length and the perpendicular distance traveled, i.e. RD, which is recorded by the measuring wheel and is equal to the circumference of the wheel times the number of rotations. But when the arm rotates about the measurement wheel and the wheel does not rotate, it sweeps out one positive and one negative circular sector, the area of which is given by the formula A equals -1/2 IR squared theta, where I is the linear position of the pivot along the arm, given as a value between -1 and +1, R is the length of the arm, and theta is the angle swept by the arm in radians. If the planimeter completes the boundary of the shape being measured, then according to the area difference theorem, the area between the shape swept by both its ends is given by the formula AR minus AL equals RD minus 1/2 IR squared theta. However, in a linear planimeter, one end of the arm travels in a straight line, while in a polar planimeter, it travels along an incomplete circular arc, neither of which encloses any area. Furthermore, in neither model does the tracer arm complete a full rotation, meaning the right-hand term cancels out as well. Thus, we are left with AR equals RD equals 2 pi r lowercase rn, where lowercase r is the radius of the measuring wheel and n is the number of rotations it undergoes. And the scaling factor, based on the dimensions of the instrument itself, is either integrated into the counting mechanism or provided on documentation supplied with the instrument itself. Now, If you place the pivot inside rather than outside the shape being measured, as you might do if measuring a particularly large area, then both ends of the tracer arm complete a full rotation, so AL becomes pi rp squared, that is the area swept by the polar arm, while theta becomes 2 pi, so the area formula becomes AR equals RD plus pi rp squared minus I pi r squared. In summary, then, the planimeter works by dividing up the area to be measured into a series of small parallelograms whose area can be directly measured by the mechanism, as well as a number of circular sectors whose dimensions are driven by the dimensions of the instrument itself and can thus be cancelled out, which, to my mind, is just absolutely genius. And this is the type of clever mechanical problem solving that I love to cover on this channel. Anyway, to finish up our look at this Ott Planimeter, as I mentioned previously, the carriage can slide along the length of the graduated tracer arm, and this is done by loosening this set screw and using your thumb to roll this knurled knob as you might on a set of calipers. This allows you to change the output scale of the instrument when working with, for example, maps or engineering drawings. For example, according to this paper slip that comes with the instrument, if the scale of the drawing being measured is 1 inch equals 25 feet, to have the instrument display its area measurement in square feet, you set the carriage to 206.4 on the tracer arm. Also included with this instrument is this check roll, which has a pin on one end and a little hole on the other. To use this, you press the pin into the surface of your drafting table, place the tracer point of the planimeter in the hole, and trace a full circle. If the planimeter is properly calibrated, then it should display the same area indicated on the reference slip, 10,023 square millimeters or 15.53 square inches. We also have a small tube of spare tracer points and a flathead screwdriver for maintenance and adjustments. Many planimeters came with other accessories, including a dust guard for the readout mechanism and a magnifier to help more accurately trace the line being measured. There were also different versions of the basic planimeter design that could integrate, differentiate, and find the square root of the curve being measured and the first and second moment of area of a closed shape. A related instrument is the opposimeter, also called a curvometer or mylograph, which allows you to measure the length of a curve, such as, say, a road or a river on a map. However, all these instruments are well beyond the scope of this video. And that, dear viewers, is a brief overview of planimeters, a type of instrument that I had actually never heard of until I stumbled upon this example. And I'm glad that I did, because this was an absolutely fascinating one to research and to present to you. So I hope you enjoyed it. Anyway, I will see you next time, another video where we'll look at yet more fascinating instruments and other devices just like this one. Until then, I'm Jean Messier from Our Own Devices. Have a great day.